Today's lecture will be about Bell non-locality. So it is a feature of quantum mechanics, but not only quantum mechanics actually. It says something more than only quantum mechanics, but we'll get to that later. So I want to start my lecture with a game. So I think if you play this game, then you will understand the concept of Bell non-locality a bit better. It's called the CHSH game. It's named after 4 people: Clauser, Horn, Shiny, Holt. Let me first explain the game, and then I'll explain how we will play it. So we have 2 parties. We have Alice and Bob, of course. Alice and Bob both get a random input bit. They get a 0 or a 1, which we call X or Y. Then they can output either a +1 or a -1. And the goal of Alice and Bob is to try to give different outputs every time if X is 1 and Y is 1. So if both of their inputs are 1, they want to output a different output, A and B. But if the inputs are different than 1 and 1, they want to output the same output, right? So there are 2 rules. No communication is allowed. So if communication were allowed, this would be an easy task, right? Then they would just communicate what their X's and Y's were, and then decide on what output to give. So no communication is allowed. They are separated by a huge distance, for instance, or some other means by which they cannot communicate. What is allowed is they are allowed to use an external source. So what I mean by an external source can actually be anything. It's just, it could be the time. They could look at the amount of seconds at the current time. And then if that is an even number, they could output +1. If it's an odd number, they can output -1. Or they can look at the intensity of a star, the sun, for instance, and then use some measurements to output a + or a -1. It doesn't matter. As long as they don't communicate with each other, everything is allowed. Okay, so let's reformulate this goal that we have. So the goal is if the inputs are 1 and 1, then they give different outputs, A and B, and they give the same output if X and 1 are different. So another way of saying that is this. We want to maximize this number S. This number S is equal to 4 terms, and I will explain what these 4 terms are. So for instance, S01 is the average of the product of the outputs A and B when X is 0 and Y is 1. So in practice, what we do, we run this for a lot of rounds. So say we do this 100 times, we give 100 inputs to Alice and Bob, and we get 100 outputs of Alice and Bob, and then we can calculate the average of the product of the outputs every time that X was 0 and Y was 1. That is S01, and similarly for the other ones. And then we add them up like this. So 0, 0, 0, 1, and 1, 0 have a plus in front of them. And S11 has a minus because if we think about it, so we want that the outputs are different if X is 1 and Y is 1. So that's this case, S11. If they are different, that means that 1 is plus and 1 is minus. Or, yeah, so A is plus, B is minus, or A is minus, B is plus. So the product will be -1, 1 times -1. So that means that if they try this strategy, that means that S11 will be -1. The average you expect to be -1. So minus S11 will be +1. So this will raise the total value of S. And similarly, if X is not, so if X and Y are not both 1, so these 3 cases, you want them to output the same output. So that means that these 3 S's here will average to 1, because if you have the same output, you will have 1 and 1, so the product is 1, or you will have -1 and -1, and the product will still be 1. So that will also raise the value of S. So another way of saying, of phrasing our goal is to say that we want to maximize S, this value S. Okay, so just notice that S is actually at most 4 and at least -4. We can see that because, well, the average can be at most 1 and at least -1, of course. So in the the best case scenario, you will have that S00, 01, 10, they're all 1, and S11 is -1. So if you add it up, you'll get 1 plus 1 plus 1 minus 1 is 4. So S is at most 4. Okay, so now I will get to the interactive part. So I want you guys to play this game, but first I want you to think about it. I want you to come up with a strategy, and you can just, I'll let you discuss for a few minutes how you want to do this. So remember, we want to maximize S, and S could be 4. So you're trying to think of a strategy where S is as big as possible. So this is how we'll do it in practice. I will first let you discuss for about 5 minutes. Anyone can say whatever they want. We'll try to lead the discussion a bit so it doesn't get too chaotic. So you can discuss on the best strategy, and you can decide who is Alice and who is Bob. Then the game starts. So what I'll do I'll send a 0 or a 1 to Alice and a 0 or 1 to Bob via the private chat, via Zoom. I'll let everyone know as soon as I send them. And then Alice and Bob get 5 seconds to come up with a +1 or a -1, and they send that back to me. And then I register that. So the rules are that the two people, Alice and Bob, are not allowed to communicate with each other. And the rest can do anything, right? So the other people can act as sources. They can, for instance, suggest a +1 or a -1 to Alice or Bob, or they can do something else. It depends on the strategy you guys come up with. Yeah, they act as a source. But the other people, besides Alice and Bob, they're not allowed to facilitate a communication between you, right? So Alice is not allowed to talk with a third person, and that third person transmits the message to Bob. That is something that is not allowed, right? So no communication between Alice and Bob. And we do this about 20 times, and then so we get 20 inputs, 20 outputs, and then I'll calculate S for you, and we'll see how good you guys do. So here, here's a summary of the game again. So we want to maximize S. Try to get it to 4. So, okay. So I'm going to leave it to you guys. If anyone has an idea, please say so. So does anyone have an idea how you would do this?
Oh, we have a comment in the chat, Frits.
Oh, we have a comment. Let's see if I can.
Is it allowed that Bob knows that Alice will always output 1?
Yes, that's a very good question. Yes, that is allowed. So that is a strategy you can agree on. You can say that one of the two always outputs a 1 or always outputs a -1. And the other person can know that. Yeah, so that's true. Yeah. So that would be a possible strategy. You could say that Alice always outputs a 1, and Bob knows that, and Bob does something else. Maybe he randomly outputs a number. Any more ideas, anyone?
Another comment, must they give the output at the same time?
Yes, they must approximately at the same time, yes. So I will announce when I give the input. They'll get the input at the same time, and then they have 5 seconds where they can enter their output. Do we have any volunteers for Alice and Bob?
Choose freely, Frits.
Yeah, I think I should. No volunteers.
I can be Alice.
Yes, I was hoping a student would volunteer. But else, would also be possible. Ah, we have a volunteer for Bob. Man Jun Cheng wants to be Bob. Thank you. Why don't you want to be Alice? Bob is also fine, but does anyone want to be Alice? Okay, maybe Naresh wants to be Alice. Are you still available?
Yes, yes, I am available to be Alice, but if some other student wants to be Alice, that should be fun.
Yeah, that's pretty easy. All you have to do is just read my plus or read my 0 or 1 that I send, and then send back a plus or minus 1.
Yep, yep.
Okay. Well, then let's do it like this. So Naresh will be Alice.
Yes.
And Jun Cheng will be Bob.
Okay.
But first, I want to give you a few minutes to just discuss a strategy. So you want to try and maximize this S. You want to give me the same output. So you want to give me a different output when X and Y are both 1. And in all the other 3 cases, you want to give me the same output.
Yes. So I can discuss the strategy with Man Jun Cheng now, right?
Yeah.
Okay.
Maybe Man Jun Cheng wants to unmute himself. And
No, that's fine. I think we are trying to discuss over the chat.
Okay. You can also discuss in public so everyone can hear.
Oh.
And
Okay.
say what their opinion is. Maybe someone else has an idea. You can also put it in the chat if you don't want to speak out.
But you are the one who is giving inputs, right? So we don't want you to know our strategy.
Oh, okay. So that's it's okay if I know your strategy because I will just give random 0s and 1s. It doesn't matter.
Okay, okay. Okay.
Oh, we have a question. Can the
Yes.
source know something from Alice Bob? It's allowed to know everything from Alice and Bob except what their input is. So the source doesn't know what the input is. It doesn't know if they got 1 and 1 or 0, 1, whatever. But the source and Alice and Bob, they can have a predetermined strategy.
We are trying to discuss the strategy over chat actually, if that's okay.
What is being discussed?
Oh, okay. So we are just wondering if one of us should output 1 and the other outputs the same input as they receive.
But the input is 0, 1 and the output is plus or minus 1. So how will you?
Yes, yes. So if I output 1, the other person can output whether if he receives 0, he'll output 1. If he receives 1, he'll output plus 1.
Okay. Yeah, sounds like a strategy.
Okay.
So if you agree on that, we can do that. Or you can do that.
Is there any other strategy that someone wants to suggest to us? Okay, someone says that if we always output the same, then we will win with 75% chance.
Yes, that is true. Yeah, but is that the best you can do? That's the question. Right? Because
okay.
You can try to compute this S value. Yeah.
Okay.
So their intent says if Alice does plus 1 for 1 and minus 1 for 0, and Bob does the opposite, would that work? Maybe.
Well,
does that sound like a good strategy? Because so if you're saying that Alice does something and Bob does the opposite, so that means that if they get the same one,
we output the opposite, right?
Well, I don't think that Darren means that that they output the opposite. It's just that Alice outputs +1 for 1, but Bob would output -1 for 1.
Okay. It is still, it seems to be still, we end up getting 75% chance.
Yeah.
Okay.
So I'll give you just another minute to discuss.
We are gonna do the, I guess that the strategy that we okay, let me confirm the strategy with Bob.
I'm
So
having some
Ethan-
technical difficulties, sorry.
Ethan, you're asking, can you see the goal of the experiment again? I'm pretty sure
Yes.
that will become clear in a moment.
So the goal, they want to have the same output unless they both get input 1 and 1. So you want to maximize this S value here. So we have a comment, if you get 0, put 1. If you get 1, ask the source to randomly give an answer. Yes, that is also a strategy. Naresh,
Yeah.
did you make a decision which strategy you want to use?
So I'm just waiting for Bob to reply.
Okay.
I'll confirm once he says something. Okay, perfect. So the strategy is the following. I'm the Alice. I'm gonna output +1 for 1 and -1 for 0. And Bob is going to randomly output either +1 or -1 irrespective of his output input.
Okay. Yes. Okay, well, we can start doing that. So this is what I'll do. I'll send the bits to Bob and Alice. So yes, the first bits have been sent. And I'm waiting for the answer.
So my answer should be visible to everyone, or is it just to Frits?
No, just to me, actually. Yeah, you don't want Alice to see, you don't want Bob to see your answer.
Oh, unless we are outputting at the same time. Okay.
Yeah, okay. So it's hard to output at the same time. So better keep it secret.
Yes, yes.
Yes, I got the answer. So now the next bits. Thank you. Okay, let's do the 4th round. So I'm waiting for Alice to respond. Thank you, Alice. And the 5th round, the 6th round. So I'm not going to do 20 rounds because due to some technical difficulties, this is going to take too long. I'll go up to 12. And the 7th round. So while everyone is waiting, you can try and think about a better strategy or try to think what you expect that S will be with the current strategy. This is round 8, round 9, round 10, round 11, and round 12. Okay, we're done. Well, just to be sure, let's do 2 more rounds. Else we have, our statistics are a little bad. Okay. Yes, we're done. So let me show you the results. Yeah, so here I recorded all the inputs and outputs that I gave to Bob, all 14 of them. And here we see the outputs. So these are the inputs, these are the outputs. And then what we get is an S value of 2.1, which is, well, not very close to 4. It's it could have been 4, but well, it's pretty good. Okay, so let me go on with my presentation and talk about why we're doing this and what this means and what it has to do with quantum mechanics. So as we know, S is at most 4 and at least -4. But we will show that actually under something called local realism, that S is can actually not become 4, but is bound between -2 and 2. Local realism is actually what we're doing here in this game. So it means that everything is classical and we're not using any quantum systems, but I'll get to the precise definition in a moment. So as we saw actually in our experiment just now, the S value was just a bit above 2. It was about 2.2. So if we had better statistics, if we did like 100 rounds, this would not have been possible. So unfortunately, we got a bit higher than 2. But if we had more rounds, this would not have been possible. And I will show that in a second. So actually, if you play this game classically and you have enough rounds, then you can never get a value above 2. So whatever ingenious strategy you come up with, it's never possible to get a value better than 2. And actually, one strategy to get to this maximum is just by having Alice and Bob output a +1 every time. So it doesn't matter what their input is or what the sources do, they just say +1 every time. And then as you can see, well, if they output +1 every time, then these 4 values here will all be 1. So we'll get 3 minus 1 is 2, which is already the maximum value. So actually, in this game, it didn't really matter what your strategy was. You could have chosen the simple strategy of outputting the same thing every time, and you would have done the best that you could. Okay, so now let's get to local realism. What is it? So as you know from the first few days of this camp, that quantum systems are probabilistic. So a quantity takes on value after you measure it. It's not that everything has a certain value, a certain speed or spin, and then if you measure it, you just get that number. No, it's if you do the measurement, it assumes a certain value. So this is very key to quantum mechanics. And what quantum mechanics does is it gives you a probability that you will get a certain measurement result, right? So that's the only thing you can know. It's so it kind of seems like quantum mechanics is incomplete because you can only get the probability of certain measurements. It doesn't say what you will get. So a lot of people, like in the beginning of the previous century, thought that quantum mechanics was incomplete and there should be a better theory. The better theory should have some kind of hidden variables that we cannot see with quantum mechanics, and these hidden variables would account for the probability. So if we know these hidden variables, then we would be able to give a complete description of nature and we could predict everything with certainty. So Einstein in 1935 was actually a bit against quantum mechanics because of this probabilistic nature of quantum mechanics. And together with his colleagues Podolsky and Rosen, he argued that quantum mechanics is actually inconsistent with something called local realism. And local realism is actually something that sounds very natural. So what it is, technically, is 2 things. So all measurement outcomes are predetermined. So, which is like in the beginning of the previous century, that was pretty obvious. It's obvious from classical mechanics that everything has a fixed position, a fixed speed, etc. So everything is predetermined. And of course, information can travel at most at the speed of light. Those things together constitute local realism. And it was pretty natural around this time to assume that nature would have to assume this. But actually, later, like in the 60s, John Bell proposed an experiment that is not compatible with local realism. So we had a certain game which is very similar to the CHSH game that I just explained. And you can show, using quantum mechanics, that it is possible to get a value greater than 2. While if you have local realism, it's not possible to get a value greater than 2, as I will show in a moment. So if you can do this experiment, such a Bell test, and you get a Bell violation, you get an S value greater than 2, then you automatically know that nature is not local realistic. So it satisfies Bell nonlocality. This is the Bell nonlocality that we mean. It means that nature does not satisfy local realism. Okay, so let me get to the proof of why S is at most 2 when we assume local realism. So let's assume local realism on this slide for now. What that means is that we can consider so-called instructions, and we denote this by the Greek letter lambda. And these instructions, they describe both the strategies that Alice and Bob choose in the game and also what the source does. So it's a combination of these two things. So actually an instruction is just a list of 4 numbers. It tells you what Alice and Bob will output when they get a certain input. So Alice has 2 numbers, which we call a lambda 0, a lambda 1, which is her output when the input is 0 or the input is 1. And we have the same thing for Bob. So the fact that we have these 4 numbers follows from local realism, because local realism means that they cannot communicate, right? Because they cannot communicate faster than light. So if they're sufficiently far apart, then we can assume that Alice's outputs do not depend on Bob's inputs. So that's why we can write down what Alice will choose as her output, given a certain input. So we have these instructions, and then we also have the probability of a certain instruction lambda. And this probability of lambda is like the probability that Alice and Bob choose a certain strategy in a certain round, and it also depends on what the source does and the rest of the environment. Okay, so recall what S is. I wrote down the formula again. Now what we can do, if we take one of these 4 values, S, X, Y, so X and Y are both 0 or 1. If we want to find out, so remember that S, X, Y is just the average of the product of the outputs. So the product A lambda X times B lambda X for a certain strategy lambda. And if we multiply that with the probability of a strategy lambda, of an instruction lambda, sorry, and we sum over all instructions, then we get the expected value of SXY. So now if we write out the entire formula for S, we get 4 terms, and it looks like this. And now we do a neat trick. We look at these 4 terms, and we can rewrite them. You can check that this is true. So the quantity here in the straight brackets equals this down here. And now we have a nice observation, because, so assume that B0 and B1 are different from each other. No, sorry, let's assume that B0 and B1 are the same. That means that this difference here is 0, so this term disappears. If they are the same, then they're both 1 or both plus 1, both plus 1 or both minus 1. So this value is plus or minus 2. A0 is plus or minus 1, so the whole thing is plus or minus 2. And now also, if B0 and B1 were not the same, so 1 is plus 1, 1 is minus 1, then this thing disappears, and then we only have this term. And then if you take the difference, you will get plus or minus 2, and you multiply it by plus or minus 1. So this whole thing equals plus or minus 2. So we see that whatever the values of A and B, this will always equal plus or minus 2. So if we sum over all lambdas, we multiply the probability of lambda, then we get that S is actually, okay, yeah, that S itself is actually between minus 2 and 2. Because for every single lambda, it is minus 2 and or 2. So the average of all those numbers will be somewhere between minus 2 and 2. So here we've actually proved that if we assume local realism, which is very natural, at least 100 years ago, then S is always between minus 2 and 2. Okay, but now something nice happens if we introduce quantum mechanics, because then we can get a larger S that is greater than 2. In fact, we can get an S, as I will show in a moment, that equals 2 square root of 2, which is greater than 2. And how we do this in practice is that Alice and Bob, in order to determine their output, is they do a measurement on a quantum system that they receive from the source. Okay, so this is the setup with Alice and Bob. We have a source between them, and what the source does is it creates a certain state phi plus, which is this state here. It is a state of 2 qubits. I think you've seen something like this Tuesday. So what it does, the source, is it sends the left half to Alice and the right half to Bob. So what happens is that Alice either measures a 0 or she measures a 1. And if she measures a 0, then she automatically knows that Bob is going to measure 0 too. And if she measures a 1, she will know that Bob will measure a 1 too. So here we already see that their two outcomes will be very correlated, right? They will both measure a 0 or they will both measure a 1. So you can already see that we will get a high value of S in this case. And this is something that is not possible in classical physics because you cannot write down such a formula as this. I mean, sorry, you cannot. You really need a state like this, which has entanglement. So without going into too much detail, just by showing what's done, we have 8 different measurements. So Alice, when she gets input 0, she measures in this basis, the 0, 1 basis. If she gets input 1, she measures in the plus or minus basis. Maybe you remember from Tuesday this diagram, how we can represent this basis. So 0 and 1 are just the x and y axes, and plus and minus are these this red basis. And then Bob has actually uses the green basis when the input is 0, and he uses the purple basis when the input is 1. And then depending if which one they measure, they will output a +1 or a -1. So this is how Alice and Bob will do this. And the calculation is pretty long. You can find it in the lecture notes if you're interested. But just to give an idea, you have to calculate probabilities like this. So for instance, if the inputs are 0 and 0, so in this row and this row, what is the probability of getting an output +1 and +1 from Alice and Bob? Well, that means that we have to calculate the probability that Alice will measure this 0 and Bob will measure this state pi divided by 8. And it looks like this. Born's rule, you have to calculate the inner product of these two states with phi plus. So I won't do the calculation, but you will get 2 square root of 2. Yeah, okay, so this is very nice because we have shown that if we assume local realism, which is what happens around us classically when we played the game at the beginning of this lecture, that was in a local realist setting, and you can only get a maximum value of 2 for S. But as was shown just now, you can get a value greater than 2 if you use quantum mechanics. And in 1982, Aspect was able, and his team was able to show this Bell violation. So the experiment I just explained, he was able to show this experimentally. But there were some loopholes. For instance, it wasn't very clear if Alice and Bob were really separated far enough, if they really weren't communicating. It wasn't possible to say this with certainty. So only in 2015, 3 different teams actually in the around the same time showed a Bell violation, but without loopholes this time. So they could be pretty certain that the measurement they did was correct, and that indeed the conclusion is that nature is non-local. So it took a while to do this experiment, right? Because in 1935, Einstein proposed this, and in 2015, it was proven. So 80 years. I think there are 3 consequences of this Bell non-locality. One is philosophical, right? It's just amazing to see that you can get a value greater than 2 by using quantum mechanics. and there's this strange non-locality thing happening. The second consequence, well, it's a confirmation of quantum mechanics, right? It's an experiment predicted by quantum mechanics, and finally in 2015, we were able to prove this theoretical result, so it actually proves that quantum mechanics is true, or it confirms, it affirms that it's true. And the third consequence is that it also has some applications to some cryptographic tasks, like quantum key distribution. It actually, if you incorporate this into quantum key distribution, which you had a lecture about yesterday, I think, then you can actually make it safer, more robust against attacks. Okay, thank you. This was my lecture. If you have any questions, please let me know. You can speak up or put it in the chat. But thanks for your attention.